Hello, everyone. This is Hanwen from Sydney, and I'm so excited to share our recent work.
But we
Sorry, pardon?
no, it's fine.
Oh, okay, cool. I'll just continue. Yeah, I'll talk about our recent research on coin flipping, and this joint work with Chang, and will be appear in crypto this year. I guess for the notion coin flipping, everyone has been somewhat familiar with it. For me, it's like I usually use it to decide a minor part in my life, like where should I get for lunch? Which fish should I get for dinner? Is it barramundi or snapper? Something like this. Sometimes you may not have a pocket in your, no, you may not have a real coin in your pocket where you want to share the coin flipping result with your remote friend. You may want to do the coin flipping online or in the digital world. There are certainly some tools allowing you to do this. It's very convenient to find these tools. You only need to Google flip a coin, and as you say, there will be a mini program pop out, and the only thing you need to do is click the button, and you will see the coin flipping result. But from this slide, right below this mini program, you also see people asking questions. There are questions like, is Google flip a coin truly 50 to 50? Is Google coin flip truly random? I think those questions are truly legitimate for two reasons. First, because the entire mini program was written by Google engineers and also hosted on a Google server. If their team decided to do anything, we don't really know. That's the first part. The second part is for the coin flipping, the result is not just a minor part, just not about a minor part in your life. Sometimes it really matters and even plays an essential role in many aspects. From now on, let's just generalize the notion of coin flipping to any process that producing a random value, which can be multi-bits instead of just a binary value indicating heads on or tails on. It can be multi-bits. So from this perspective, we may see lottery as a very typical example where the entire business is built upon the coin flipping with a good quality. I mean, the lottery winner is meant to be randomly chosen. Otherwise, if some guy has the power to decide who is the winner, and that guy is not you, you don't want to be a part of this game, right? So as we say, in nowadays the price pool is quite generous. We can say we have really great stake in the quality of coin. It can be over $100 million. That's a lot of money. We can also say the importance of randomness goes well beyond the lottery example. Essentially, it plays an very important role in many aspects of computer science. I'll just give you an example in distributed system, that's Ethereum, which is the second largest cryptocurrency in the world, with a market cap of more than 400 billion US dollars. As we all know, Ethereum has been a massive network. More specifically, it has over 1 million validators. So that's a huge network. So just from efficiency perspective, it's impossible or impractical to gather all the validators together to decide the status of every transactions. It's just impractical. But Ethereum comes up with a smart solution by leveraging the randomness in a clever way. What they really did is to employ a coin flipping to do randomized committee sampling. I mean, they will randomly sample committee with much fewer number of nodes, usually on the order of a few hundreds or a few thousands, something like this, and let the committee members to take over the transaction process for the entire network for a short period. In this way, the dilemma between the efficiency and the security can be solved. The intuition behind the approach is because the process of randomly sampling a committee may use a coin with good quality. So in this case, we can have some analysis and guarantee that the majority of the committee members are honest. So essentially let a committee with an honest majority to do all this task so we can keep the system alive while make it scalable. But on the other hand, if the coin is entirely corrupted, I mean, if the adversary has the power to decide the committee members, it's possible maybe all the committee members are corrupted. In that case, the whole system may be doomed. The importance of randomness also goes well beyond even goes out to the computer science. We can see several examples where randomness matters to our social justice and social fairness. Let's say there are many countries use common randomness in jury selection. I mean, maybe the authority will leverage a common randomness to sample some citizens from a pool for form a jury for each cases. And in many states, in the United States, they use common randomness to break a perfect tie in an election. I mean, if there are multiple candidates winning exactly the same number of votes, in that case, they can just flip coin and decide who is the final winner. And there's also a technique called a risk limiting audit. This technique uses random sampling paper ballots to statistically confirm that the reported election outcomes is correct. This technique has been employed in the United States presidential election in the previous rounds for several times. And we can imagine in these cases, if the randomness is ever corrupted, for example, in jury selection, if one guy can decide the randomness and thus has the power to just decide are the committee members, who are the jury members for any special case, then that guy will have the power to decide how a criminal case may be finally settled. That's a great power, and we don't like it for sure. There are certainly more applications. For example, in the most famous anonymous communication tool, the Tor, it is essentially employ common randomness to improve its security. And also in gambling, for sure, because we want randomness in gambling, because that's where the fun comes from. And there are many other applications. For me, I personally believe randomness should has a role in any randomized distributed computing examples. And for example, like federated learning and decentralized AI. And I believe you can name more. Okay. So given all these considerations, we can acknowledge that for this serious stuff, we are not satisfied with an arbitrary mini program provided by Google. It's not meant to be suitable for serious stuff. We must be more serious about the coin flipping when its result really matters. So surely there are some organizations standing out trying to provide coin flipping with better quality or better transparency. There's a typical example in the typical example of the lottery. We can see the organization running the lottery will periodically have a ceremony on leaf and using some special equipment for drawing some balls from a pool, and the digits on the pools can decide the final winning ticket. This process means to be provide a coin with good quality and better transparency. But this is just a special purpose. And there's other general purpose of a common randomness, which is, for example, there's one provided by NIST, which is the National Institute of Standardization Technology, which is an American government agency. They provided something called random speaking. You can see it as a public API, and everyone can call it and get randomness from the API. And if two people on the different locations of the world, if they decide to call the API with, let's say, the same time step, they can get the same randomness. That's the functionality of this API, which is super powerful and seemingly useful, because you can imagine with this API, maybe all the examples I mentioned before can simply call it and to get the randomness they need from their examples. Okay, so but despite these organizations providing this randomness, maybe backed by authorities, where they are authorities themselves, and they should have made some efforts to make their results more trustworthy. But my question is, can we always trust them? or are they always trustworthy? If the answer is yes, I guess Mr. Snowden might have a different story to share with us. Actually, there are some scandals. In 1980, there's a lottery organization in Pennsylvania. They were caught by the authority because they misbehaved. They maliciously manipulated their machine such that their drawing machine will output a ball with certain digits with a larger probability than others. So in this way, they can manipulate their results, their winning ticket. And it's a bit funny because the authorities noticed this issue only because they produced the winning ticket and the 666, which is just so suspicious. I don't know how long they had been running this fishy business, but I guess if the organizers were smarter in manipulating this machine, like just avoiding these trivial patterns, they may be able to run in this fishy business for a much longer time. Okay, and even for well-respected NIST, they do also have a stain on their reputation. They once published a cryptographic algorithm for standardization purpose, but that algorithm indeed has a backdoor that enables the authority, or let's say enable NIST or the US government to monitor the private communication between their citizens without being noticed by leveraging the backdoor. And this issue was only resolved after several years. It has been published and being observed. So given this status, we know randomness is really, really important. But the providers, even they are well respected and backed by authorities, they may still be incentivized to misbehave. So a natural solution is like we should invite more people to regulate this process, to audit these services to ensure they behave honestly. But there are some inherent challenges in audit this service. First, it's really hard to detect if a single string is honestly sampled. Let's say if I just decide to present you one bit, the bit can be either 1 or 0. How can you tell this one bit is obtained by uniformly sampling from 1 and 0 instead of just being decided by myself arbitrarily? You don't really know. And the second thing is, it's really harder to prevent the provider from leaking the coin result to some privileged parties. I mean, even you have some magic method to enforce the final result is uniformly sampled, but the provider may just leak the sample result to from other parties, some privileged parties in advance. Just like in lottery, even the winning ticket is decided uniformly random. But if the provider, the organizer, already informs the final winning ticket to someone else, and if that party is not you, you still don't like this lottery. You don't want to buy a ticket from them. This is the issue. So we're really not in a good place. We know randomness is important, and providers tend to be fishy, but there's inherent challenges to audit their service to enforce the providers to behave honestly. So we look at the computer scientist solution because we love to solve problems. We love to address all the challenges by using algorithms and the protocols. We don't care about regulations. Just kidding. Okay, so there's a notion called common coin. It works like this. In the very beginning, there's a network with multiple computers where they can be held by different entities or different people and distributed across the entire Earth, let's say. And they can run a distributed protocol called common coin together, such that at the end of the protocol, everyone will see the same random value. And this is ensured by the nice properties called termination and agreement, which says everyone at the end of the protocol can see the same random value. And there are some other nice properties which describes the quality of the coin. These properties are unpredictable and BIOS resistance. Unpredictable means no one can know the random's value in advance up to some point. And the BIOS resistance, just from the name, it means no one can bias the distribution of the final randomness, where let's say the final randomness is supposed to be nearly uniformly distributed. These are nice properties about the common coin. And it's also important to emphasize that in a distributed computing protocol, in the distributed common coin protocol, we can ensure all these four nice properties, even when even when a portion of the network are corrupted by some adversary. I mean, some nodes may be just Byzantine and can behave arbitrarily. Despite that, the protocol can still ensure all the four properties I just introduced. Okay, this is common coin, and it's really a beautiful solution because it handles challenging by using algorithms and protocols. We don't need to blindly trust any entities in the world. But there are some prices. Although it's a beautiful solution, but until very recently, common coin protocols are really expensive. Before going into too much details, I'll just clarify the network models we work in. A network model is just is you can understand it's an abstraction of the network the protocol is deployed in, and it also describes the quality of the communication channels between different nodes in the network. A popular model is called a synchronous model. It says that every message sent by an honest node can be delivered to another honest node within a public known bound. Let's say delta in this slide. The knowledge of delta, of course, is very useful for protocol design, but on the other hand, it's problematic in practice because internet is not synchronous unless we are okay with a super large delta, which can be on the order of a few minutes. But in that case, it means if you adopt a delta with a few minutes, your protocol is gonna be super inefficient. Just imagine a protocol, just one round back costs a few minutes, and if protocol maybe a few tens of rounds, then you're gonna need to run it for hours. We don't want it. So there's an alternative modeling called asynchronous network. It basically eliminates assumption on the message delivery time bound. It just requires every message sent by an honest node can be eventually delivered to another honest node. That's the only one assumption made by the asynchronous network model. The benefits of asynchronous network is better captures the real network. So a protocol in the asynchronous network is more resilient to network fluctuation. And the side benefit is because we don't need to worry about the timeout anymore. So the protocol in the asynchronous model is much easier to implement. It's the benefits of the asynchronous model. So this is our main focus of this talk. With the asynchronous network model in the mind, let's look at the picture how common coin protocols have been developed in the asynchronous network setting. In the early results, they are mostly theoretical oriented and focus on the information theoretical setting where the adversaries has unbounded powers. It's not surprising to say all these results are impractical because their communication complexity can be as high as n to the seventh power. So, and whereas n is the network size. So we know for this kind of a for a protocol with such kind of a communication complexity, it cannot be used unless the n is super small, like 2 or 3. Unless that, beyond that, I can say it's impossible. Actually, the study in asynchronous common coin has got stuck for a while. But in recent years, due to demanding applications in the blockchain setting, there's a resurging interest in developing more efficient common coin protocols. In 2020, there's a paper on CCS published common coin design in the computational setting, where the adversaries is computationally bounded. And it significantly advanced the communication complexity compared to previous theoretical results. But it achieves the communication complexity of n to the fourth power, and the round complexity is linear to n. But still, although it's a clear improvement compared to the previous result, the n to the fourth power, this kind of communication complexity also makes the protocol impractical, even for moderate scale of n. So, so the main question left by this work is how to improve the communication complexity and also round complexity, and also from different perspectives. There are great many works following this work, focusing on improving the common calling protocol from different perspectives. I'm not gonna introduce all these works in greater detail, but a quick summary is all these works so far they still require cubic communication complexity. And I want to say cubic communication complexity is really huge. For better understanding, I just draw a communication pattern for one round in a cubic communication complexity protocol. And you can see that even in one round, everyone in the system needs to multicast an ON size message to everyone else in the system, which makes the protocol cubic. On the other hand, ideally, for all the consensus and the common calling, we know there's a lower bound. If we assume the adversary is adaptive, there's a lower bound which says the protocol needs quadratic communication complexity. I mean, there's a huge distinction between cubic and quadratic, because in a quadratic communication complexity protocol, everyone just needs to send a constant size message to everyone else. I also did a rough estimation to show the difference regarding the concrete cost. Let's just assume the message unit is merely a few tens of bytes, and we can say just in one round of communication, and when n is like a few thousands, like 1,000 or 2,000, just one round of communication in the cubic protocol is gonna cost you a few hundreds of gigabytes, while quadratic communication complexity protocol, the concrete cost is well below 1 GB, usually a few tenths of megabytes.
So Hanwan, so in this
Yeah,
order of n squared, so you say it's constant size messages, and
yeah.
you're only sending it to a subset of the parties, which is like a constant size subset.
No, everyone.
Ah,
Everyone, you multicast it to everyone.
okay, so so the only, because you say, oh, this O of n, O of one is just again size, is it? Okay, I see. So it's a constant size messages that you send to everyone. That's
Yeah,
the improvement that gives you n square.
yeah. That's the communication pattern in N square protocol.
Okay, got it. Thanks.
Okay, cool. So this huge difference. So I think we are very right to ask the following question. Can we design an asynchronous common calling protocol with optimal quadratic communication complexity? That's our key problem. But at the same time, we don't want to trade off anything. We don't want to sacrifice anything. We want to maintain or preserve other optimal metrics, like including the protocol has to be constant round and tolerate up to 33% of Byzantine nodes, and which is optimal for all asynchronous consensus. We want everything to be optimal, so the final result is going to be asymptotically optimal common calling in asynchrony. That's why we limit in our title. Okay, so let's start our journey for building this optimal asynchronous common calling protocol.
So Hanwan, so this optimal communication complexity is what? It should be n square. Is that the optimal that you want to achieve?
Yeah. As I said in this slide, although I didn't speak it out, there's a n square communication complexity applies to any consensus or calling protocol where when the adversary is adaptive, only for adaptive adversary.
Okay.
Yeah.
So you also want to do adaptive?
Yeah.
So you want to do adaptive, you want to
yes.
be constant round.
Yeah, adaptive, constant
And
round, quadratic communication complexity, and 1/3 of corruption, 1/3 of a Byzantine of corruption.
okay, I see.
Yeah.
Okay.
Okay.
And so in terms of corruption, do we know any other result that is lower corruption and still achieves this optimal communication?
No, we don't know it.
Okay. Good. Okay. Good.
Okay, so let's just walk through our idea. In the very beginning, I'll illustrate the basic design idea of a common coin. So everyone will have some sense how common coin protocols are built in previous design, or let's say in all designs. I'll illustrate the basic idea with an example, which is gambling, and because where we need randomness for fun. And in a typical case, when we want a common randomness in gambling, the typical approach is just to have one player roll a die, so the dice rolling result will be a common randomness for the game, at least for the round of the for that round of the game. But there's one issue. Maybe the guy who rolls the die is a master, really good at rolling the die, and so has the power, his ability to decide his dice rolling result, like this gentleman. So we want to have a more fair game and prevent this master from deciding the dice rolling result. So let's go with one revision. We let everyone roll a die. Let everyone roll a die. Let's say they are doing this independently, and we will have the final result of the common randomness needed for the protocol, needed for the game, and the summation of all the dice rolling results and model 6. So the idea behind this approach is like and as long as there's one good guy in the game, and the good guy will contribute a will contribute a uniform randomness, and like following the similar idea of one-time padding, this uniform randomness after summation will make the final results also distributed uniformly randomly. Okay, this is any question? All good? All good. Okay.
All right. Can comp the adversary bias the result in this case?
Yeah, that's why it is revision 1. Okay.
Okay, spoiler. Okay, sorry.
Okay. So as Michael has already observed, don't forget we have a master around the table. Maybe the master is fast enough to see the dice results of other people, and after that decide its own dice rolling results. In this way, because the master can adaptively decide what the result is of his own dice rolling, so he has ability to fully decide the result even after summation. So we wanna also prevent this kind of master from biasing or from controlling the dice rolling result. So we go with revision 2, where we use a dice cover to prevent the master from seeing other people's dice rolling result. It works like this. First, everyone roll a die under the dice cover and let it settled. And but after all the dice after everyone has finished the dice rolling, and we remove the cover gently without disturbing the dice rolling results, and then we apply the summation strategy again to obtain the final roll, to obtain the final result. In this way, even the master, it cannot adaptively choose his own dice rolling result according to other people's dice rolling result. So in this way, essentially we have a secure solution of a common coin protocol. Okay, that's actually gives the basic template or the framework of constructing a fair common coin protocol. Any question?
Yeah, what if the master not like the adversary just not show their own result? Wouldn't that bias the outcome?
Yeah, but you just say every players are sitting around the table.
Okay.
If the master refused to do so, we can
I'll
other.
kick him out and then do it again, right? Okay.
No. We don't need to kick it out.
Oh, we just
the-
force the cup to be removed.
Yes.
Okay. Interesting.
Yeah. So a lot of details has been there. So in the digital world, when we want to have a common coin protocol, we just need to translate all the ingredients I just introduced. Let's look at all the ingredients we need. First is the dice rolling, which in the digital world is super simple and standard. We only need to sample random value locally. Not much to see. But for the dice cover, it's a little bit complicated. Essentially, we're at a high level. We will need a special form of a cryptographic commitment. At a high level, a cryptographic commitment can be described by two components. The first one is a commitment algorithm, which commits the randomness to a commitment. It's like you roll a die on a dice cover, where you cover your dice on using this cover. It's the commitment algorithm. And the nice property with the commitment algorithm is hiding, which means the commitment cannot reveal anything about the randomness being committed. This is the hiding property and the commitment algorithm. And the second component is opening. In the context of coin flipping, the opening algorithm has some special form. Let's say we would like it can be executed when some honest party is willing to do so. Let's just put in a vague form. And the property associated with the opening algorithm or opening component is like the commitment can only be opened to the random value it was committed to. Corresponding to our previous example is like we must remove the dice cover gently without disturbing the dice rolling result. Okay, this is the opening algorithm and the associated property we want from this component. Is that everything? Any guess? Looks good. But don't forget about the last component, which is the table. Actually, it plays a very important role in our previous example, because we do need the table to roll a die on it, and such that our dice rolling result are visible to everyone else, and everyone has the same view on the dice rolling result of other people. I abstract a few properties about the table. Let's say, first, everyone can write to it, like everyone can roll a die on it. And second, the written things cannot be mutated. Like you once roll a die, you cannot change it. And finally, and also importantly, everyone has the same view about what has been written. Okay, like you once roll a die and remove the cover, everyone sees the dice rolling result immediately and have the same view. Usually in protocol design, particularly in cryptographic protocol design, these properties, the object with these properties is abstracted as a broadcast channel, and it is usually used as a black box in cryptographic protocol design, so we can focus on other parts like the commitment parts. But when we really want to deploy the common coin protocol in practice, let's say over internet, we must answer the problem: how to form a table over internet. We must answer the problem. So there are actually a few options. Let's explore them together. The first one, maybe we can employ some trusted server. Let's say we have, besides of a bunch of normal nodes or normal nodes, we also assume additional trusted nodes among the network. So everyone just provide their message to their nodes, and the nodes will forecast or broadcast this message to everyone else in the network. But the problem is, by doing so, we post an external trust. We no longer just trust the majority of the nodes in the network are honest. We are trust very special nodes in the network is honest. So it's an external trust. And it also posts a single point of failures, because if this server is down, we don't have broadcast functionality anymore. The second option may be blockchain, which can be better than the first option, because blockchain is maintained distributed, so there's no single point of failure. But if you decide to broadcast something by using blockchain, you may need to create a transaction and put your data in it and post the transaction on the blockchain and waiting it to be confirmed so everyone else can see it. By doing so, you need to wait a much longer period, so you are suffer from high latency. You also need to pay the transaction fee, which means higher monetary costs. That's our issues with the blockchain-based approach. So the third approach is our main focus, which is based on consensus protocol. For consensus protocol, we care about a special form. It works like this. In the beginning, every node in the system has an input, and in the end of the protocol, everyone outputs the same set, and the set contains multiple inputs. That's the form of consensus we will need for realizing the table in the network. The benefit or the advantages of having a consensus protocol than leveraging a trusted server or blockchain is that the consensus protocol, it is self-contained. We don't need any form of external trust because the security of the consensus protocol just rely on the cryptographic assumption we made and the honest participants. I mean, the security trust model is exactly the same we require for the coin protocol. So it's a self-contained protocol. And the protocol provides some nice properties, including termination agreement, which means everyone will see the same set at the end of the protocol. And there's also validity, which means the honest input will be included in the final output. So let's have a breakdown to summarize all the discussions we have. For common coin protocol, we can realize it from two components. One is cryptographic commitment with a special form, like I just introduced. The other component is consensus to form a table in the gambling example. Now let's look at the asynchronous case and let's see why the asynchronous common coin is challenging and expensive. The real reason is asynchronous consensus is challenging and expensive. There's a very famous impossibility result proposed by Fisher, Lynch, and Peterson, usually known as FLP impossibility, which may be one of the most important impossibility in the domain of distributed computing. It says that achieving consensus in an asynchronous network is impossible when at least one node may crash and the deterministic algorithm is used. Okay, so this impossibility actually indicates the consensus in asynchrony has to be designed in a fundamentally different way than their synchronous components, counterparts, because we can no longer use a deterministic algorithm. We must employ a way to randomize the protocol, to have a randomized algorithm or protocol to bypass this impossibility. And the most popular design to randomize the consensus protocol is to employ a common coin. So we have such a reduction. To build an asynchronous common consensus, we usually need an asynchronous common coin. Let's look back at our previous framework. To build a common coin, we will want a commitment and a consensus. But in asynchrony, to build the consensus, we usually need a common coin. Okay, so in this way, we have a circularity because the common coin and the consensus, they rely on each other. But for the purpose of building an asynchronous common coin, we have to bypass its circularity. So which means we must employ a less standard technique to randomize consensus. Before introducing that path, let's look back at the common path again, where asynchronous consensus employs an asynchronous common coin for randomization. In this path, the common coin used to randomize consensus needs to satisfy the four properties: termination, agreement, unpredictable, and bias resistance, like always, except with negligible probability. This is the property required by asynchronous common coin and needed by most consensus design. But because now we want to avoid this circularity, we cannot use a common coin to randomize consensus. Instead, we need to use something called asynchronous weak common coin. It's not a standard common coin we talked before. It's weaker in the sense that the three properties, agreement, unpredictable, and bias resistance, are not always satisfied. They're only satisfied with a constant probability. For example, there's a 50 chance everyone in the system output the same value, but there's another 50 chance everyone in the system output differently. This is a property of a asynchronous weak common coin. Okay, so this reduction has been established. There are consensus protocols building themselves by leveraging the so-called common coin. So from feasibility point of view, the challenging of building asynchronous consensus can be reduced to building an asynchronous weak common coin. And the existing construction method for asynchronous weak common coin, the structure is similar to that we have for the standard common coin. Again, it can be built from a commitment like before, but because now the weak common coin, it does not satisfy the agreement like always. So the underlying consensus does not need to be that strong. We don't need a standard form of consensus. We can employ a weak form of consensus. And this component, this weak form of consensus, is called information gather in the literature. The good thing is, because information gather is not a standard consensus, it's only a weak form consensus. It does not need to satisfy agreement or other standard properties. So it's not subject to the FLP impossibility, which means we can build the protocol. We can realize the information gather functionality by using some deterministic protocol. So in this way, we have bypassed the impossibility, and we have, say, a path to build the asynchronous common coin. I mean, for asynchronous common coin, we need asynchronous common consensus. Then we need asynchronous weak common coin. And asynchronous weak common coin can be built by using a deterministic protocol called information gather, where no further randomization is needed. Okay, this is actually a very complicated path and solves the feasibility of establishing asynchronous common coin. But the problem is, when we have the efficiency, where the optimal efficiency as our goal, we look at the existing design, we found that every place in this reduction suffers from cubic communication complexity. Every place is so expensive. So for our goal, if we want to have an optimal asynchronous common coin, we have to reduce the communication complexity of every part, all the three parts. This is what we did. As a quick summary, or a quick heads up, for the information gather part, we propose something even weaker than information gather. And we can show even with the weaker primitive, we can still build asynchronous weak coin. And we also applied advanced cryptographic technique to reduce the communication complexity needed due to the commitment part. And also we show a new compiler from weak coin to asynchronous consensus with only cost of a quadratic communication complexity. And in this talk, I'm gonna just focus on the first part. And I also personally believe this is the core part of this work. Okay, let's go into greater details. Let's look back at how a normal or standard asynchronous common coin is designed. The consensus part in the common coin design is more specifically usually called a subset agreement. In a subset agreement, its functionality is like this. Everyone can put an input to the consensus. And at the end of the consensus, everyone will output the same set of n minus f values, where n is the network size and f is the maximum number of nodes the adversary can corrupt. And because we are in the asynchrony, and maybe the malicious nodes never shows up, so n minus f is values in the final output is the best we can hope for. Okay, so this is the consensus component in detail for the common coin design. The rest of things is pretty just the translation of the gambling example. I mean, everyone just post a commitment to a random value chosen by themselves and provide the commitments as input to the agreement, to the subset agreement component. So everyone will end up with the same set of commitments, n minus f commitments. Then we open all these commitments, so everyone has the same set of randomness. And the final randomness is just a summation of all the open values. Just a translation of our toy example. So in this way, the final randomness value is good because we have honest contribution and the adversary cannot adaptively choosing his own randomness according to other randomness because of the commitment. Okay, but in our weak common coin design, we don't have consensus anymore. We have to employ a much weaker form of a consensus, which is called information gather, like I said before. Compared to agreement, the difference is after information gather, maybe different honest nodes will output different sets. Just look at the picture, the matrix. Like before in the previous page, we can see everyone output V1, V2, V3. The green area is their output. Everyone output the same. But in the gather, everyone may output differently. Like P1 still output V1, V2, V3, but P2 outputs V1, V2, V3, V4. They have different output set. But there's still some guarantee about their output. That is, despite their output sets are different, they must share a core set with n minus f values. Like in this example, surely the V1, V2, V3 is a core set because this set of n minus f values are contained in everyone's outputs, in every honest guy's outputs. This is the definition of a core set. And I want to also emphasize that the honest nodes are not aware of which subset of their output set is the core set, but they just know there must exist a subset which is their core set. Okay, so let's look at how we may employ this weak form of consensus, the gather, for constructing the weak common coin. First, I'll discuss the commitment phase a little bit later. Let's just say similarly, everyone just propose a commitment to the input to the gather phase. But because gather does not ensure everyone see the same set, cannot ensure everyone see the same set of commitments. So everyone may end up with different sets of commitments. Then we still run the open phase to open the commitments from outputted by gather. So everyone will see the different sets of randomness. So at this stage, we don't know. The goal is like we still wanna have some constant probability such that the honest nodes can see the same random value. That's our goal that's our goal in weak common coin, right? But the situation is because everyone have different sets of randomness. If we naively aggregating all the randomness together in the local sets, there may never be the case that different honest parties can output the same value. Okay, so to make the gather part really useful, we have to make some modification to the first phase, to the commitment phase. Like before, in previous design, in the common coin design, everyone just propose a commitment to a random value, and the random value is chosen by them all. But now in the weak common coin design, in the commitment phase must be strengthened, such that everyone will still propose a commitment, but the committed random value must be unknown to the proposer. Okay, and this requirement can be realized by some standard way, like everyone can first collect some f+1 commitments and aggregate them together. So the final aggregated commitment will commit to a random value which is unknown to the proposer. Okay, so with this in mind, because we have strengthened in the commitment phase, all the commitments already commits to a value which is unknown to anyone. So the goal can be relaxed. So if the remaining stage can enable the network to pick one commitment and take the open value as open value, because that value is already unpredictable to everyone. So we can just take that value as the final coin output. Okay. So let's look back at the stage after opening. Everyone now after opening have a different sets of randomness. now their goal is to enable the honest parties to pick the same randomness out of the outputted the set outputted opened locally. Okay, so to achieve this, the existing work proposed a very smart strategy. That says we just pick the largest value among all the open value. Any question? Okay, I just continue. The strategy is like have everyone pick the largest value among their open value. Just be remind, although the gather output different sets to different party, but the honest parties in the network, they share the same core set. And also because the gather operates over the commitments, so the core set is decided independent of the open value. And the core set has n minus f values. So there's the probability of the largest value in the core set is like n minus f over n. And when the largest value is in the core set, naturally everyone in the network will see every honest one in the network will see the largest value, and they will decide on the largest value. So they can agree on the largest value. And when the largest value is outside the core set, they may end up with different thing. In that case, they can output different values. That's the reason why the protocol realizes a weak coin functionality instead of a standard common coin functionality. Are we good? Any questions?
You can ask.
It's a bit confusing for me. So will this like how to determine what is the largest? I guess that's a kind of like a open algorithm, right? For every entity. And as a malicious node, can I just like send like craft the largest value myself and then send it to all the other nodes? I cannot.
No, because the opening phase only happens after the gather phase. So everyone already has their output set. Then we run the open.
Right.
You cannot inject some new values to the output set.
Right, sure. But for example, if you are rolling a dice, right? Let's say the largest is based on the numerical values.
Yeah,
Can
of
I
course.
just always share like the number 6 to all the other entities? So I'm always the largest?
That's the reason why we need to strengthen the first phase. The first phase is no longer just to propose a commitment to a random value. You need to propose a commitment where the underlying random value is unknown to yourself.
Oh, okay, I see. Right, okay.
Okay, are we clear?
And the hash is just to making sure that we have a uniform.
Yeah,
Okay, got it. Okay.
to kill the BIOS like a random oracle. Okay. Okay, that's the design idea of a existing weak common coin protocol. So yeah, that's just what I have analyzed. Let's look into the detail of gather. We don't really want to go into the detail, but from the picture you can tell it's super complicated. But I want to explain how it really works. But just from the picture, you can tell a quick message. Then it's a cubic communication protocol, right? Because you can see at multiple stage, everyone needs to multicast an ON size message to everyone else. So it's a cubic communication protocol. It's an expensive one. So if we ever want to make the previous design enjoy the quadratic communication complexity, we must reduce the communication complexity of this component. But unfortunately, we find that maybe the cubic communication complexity is inherent to the goal of gather, because gather wanted to ensure everyone's output contains the same core set. For realizing that, it seemingly requires every node to inform all others which set they are going to output. And this step will cost cubic communication complexity. So it's really like we have digged deeper to the bottom of everything, and we found there's a huge rock there, which is a gather, and we don't know how to crack it down. But fortunately, we realize we don't really need it. We can just bypass the rocket to get to our destination. Just recall it. In the weak coin design, all we want is to ensure with a constant probability, all nodes can say the same largest value. We realized we can have two relaxations while this goal can still be achieved. The first one is we don't really need to have everyone say the same largest value initially. Instead, we can have f+1 nodes initially say the same largest value. And after that, we can have an additional round for lighting these nodes to multicast the largest value in their local pool to everyone else. So if the largest value has been seen f+1 on its nodes, then in the subsequent round, everyone in the system can see the largest value. Like the idea is like have a part of the honest guy help the remaining honest guy. Okay, this is the first relaxation. And the second one is maybe more subtle. It's even for the f+1 honest nodes, we don't really require their output to share the same core set. We only need the set to be sufficiently well covered. I'll tell the difference in this slide. Just recall it. For common set, the standard agreement, we require everyone output the same set. And in gather, we require everyone, although everyone may output differently, but there's a core set in everyone's output. Everyone must share the same core. Everyone's output set must share the same core set. That's gather. What we are gonna propose is something we call align. It's even a weaker primitive than gather in the sense we don't require the core set anymore. Instead, we require a well cover set. Just look at the third matrix. The V1, V2, V3, the three values are the well covered set. By well cover, I mean every value in the set will be outputted by f+1 nodes, but they don't have to be outputted by the same f+1 nodes. They can output it by different of f+1 nodes. Like V1, it is outputted by P1 and P3, and V2 is outputted by P1 and P2, and V3 is P2 and P3. This is the definition of alignment, where I say the output guarantee of alignment. Surely it's weaker than both of before. Let's see how we employ this much weaker primitive in the weak coin design. Like I have mentioned, the only modification we need to, besides replacing this component, the only modification we need to make is to introduce another multicast round after opening phase. Like we have everyone in the system, after seeing the largest value after opening, multicast the largest value to everyone else. So everyone else will see the largest value. The analysis can go like this, with the constant with the probability of m minus f over n, the largest value will appear in the well covered set. And in that case, by the definition of well covered set, this largest value will be outputted by f+1 honest node. And then following this multicast round, all the honest nodes in the system can see the largest value, can see the same largest value. So in doing so, they are able to agree on the value. And otherwise, if the largest value is outside the well covered set, they may end up with different things, just like the previous construction with gather component. Okay, this is how we leverage this weaker primitive for building weak consensus. While alignment is much weaker than gather and agreement, the good thing for us is we can construct it with much cheaper communication cost. I'm gonna introduce a bit of detail about the construction. The component we used in our alignment is called a probable broadcast. It works like this. Everyone broadcasts the value to the network, and the receivers will echo receipt to the sender. The receipt is just a signature. And the sender can collect, let's say, at least collect n minus f signatures from different parties on the value. Then they can gather all the signatures together to form a certificate for the delivery of this value, which is a proof of this broadcast. It's easy to tell the computation cost for probable broadcast is linear to the network size, and we have some security guarantee. Particularly, the existence of the certificate suggests at least f+1 forever honest nodes have received the value. That's the security guarantee of a probable broadcast. So with this component, we build our alignment like this. It's a complicated protocol, and I'm not gonna introduce too much detail about it because there are quite many subtleties. But there's a quick intuition because it works like this. An honest node will only decide to output when it received like n minus f values with valid proofs. And because the security of a probable broadcast suggests that the existence of proof means at least f+1 forever honest nodes have received this value. So when someone has received n minus f values with valid proofs, so it means those f+1 values has been delivered to, each of them has been delivered to f+1 honest nodes. So they can be considered as the well-covered set in the definition of alignment. But of course, there are other subtleties, but this is the basic intuition of our protocol. In this way, we finish the first task by proposing a weaker notion of a consensus and realize it with a quadratic computation complexity. And this component, we found is sufficient for constructing a weak common coin. We surely have taken other treatments to fill the other gaps to realize our final goals. Just looking at the slides again, maybe. For the second part, the commitment used to be expensive because it usually leverages some traditional verifiable secret sharing techniques, which will require cubic communication complexity in the whole construction. What we did for this part is to employ a recent breakthrough by Sanjian Garg in crypto last year, which proposed silent setup threshold encryption. And we modify their construction for our, and improve the security and the functionality for our own purpose, and let the threshold encryption serve as a commitment in our construction. And the third part is how to build an efficient consensus from weak common coin. This part is actually quite simple, and we are a little bit surprised this simple construction hasn't been utilized before. But I think the reason is we utilized an overlooked primitive, which is a multi-valued Byzantine agreement, which hasn't been widely used, but we observe this and use this component to build a very efficient asynchronous consensus from weak common coin. That's our all treatments for realizing our common coin. Finally, let's just position this work in the literature. As we can see, this work is the first common coin protocol under a silent public setup achieving quadratic communication complexity and constant round. What I haven't mentioned before is actually back more than 20 years ago, there's one paper achieving the same communication complexity and round complexity, but it's under a private setup, which means there's a trusted party already created the coin and dispersed to the network, and the online is only consume this previously generated coin in a smarter way. I think private setup is not suitable for many decentralized applications, and it's thus unfair to compare a private setup coin protocol with a public setup one. So that's our work. And for now, in this work, we'll focus on pushing the asymptotic performance, asymptotic complexity to be optimal. So I think it's still a theoretical work. The next follow-up question is, can we make the protocol or can we design another protocol which is truly practical? And for now, we also use some classical cryptographic tools like the silent setup threshold encryption. We don't know how they can be realized in the post-quantum world. So a very interesting question may be how to design a post-quantum secure asynchronous coin with the same performance. Yeah. I'll conclude my talk here, and thanks everyone for listening, and I'm happy to take any questions.